Hello everyone, it's me Swati Malik from BSc Honors Chemistry final year. Today my chapter is metal ligand bonding in transition metal complexes. Valence bond theory. Valence bond theory was developed by Lewis Pauling. According to valence band theory, the bonding in metal complexes arises when a filled ligand orbital containing a pair of electrons overlap with a vacant hybrid orbital on the metal or metal ion to give a coordinate covalent bond, as shown in this figure. Thus, valence bond theory assumes the bonding between the metal ion and the ligands to be purely covalent. The hybrid orbitals that a metal atom ion uses in accepting the pair of electrons from the ligands are those that point in the direction of the ligands. Valence bond theory successfully explains the structure and magnetic properties of coordination compounds. The silent features of the theory are shown below. First is the central metal atom or ion in the coordination compounds offer a number of vacant orbitals which is equal to the coordination number of the metal atom for the formation of coordinate bonds with the ligand. The approximate atomic orbitals s, p and d of the metal hybridize to give a new set of orbitals of equivalent energy called the hybrid orbitals. These hybrid orbitals are directed towards the ligand depending upon the geometry of the coordination complex. Third is the d orbitals involved in the hybridization may be either inner n-1 d orbitals or outer n d orbitals. Thus, hybridization in case of octahedral complex may involve d2sp3 or sp3d2 depending upon whether inner or outer d orbitals are used for hybridization. The vacant hybrid orbitals of the metal ion overlap with the filled or occupied orbitals of the ligand and form a coordinate bond like LM, ligand metal bond. Let us take example to highlight the feature of valence bond theory to complexes with coordination number 4 and 6. Complexes with coordination number 4. Coordination compounds with coordination number 4 are well known. Complexes with coordination number 4 can be either tetrahedral or square planar depending upon whether the hybridization is sp3 or dsp2 respectively. Some of the most commonly found examples are described below. First is formation of NiCN4 whole 2 negative ion. The oxidation state of nickel in the complex ion NiCN4 2 negative is +2. We can represent the electronic configuration of Ni2 positive ion by losing 2 electrons from the outermost 4s orbital. Electronic configuration of Ni, which is having atomic number 28, is 18 argon 3d8 4s2. Thus, the electronic configuration of Ni2 positive ion is 18 Ar 3d8. Thus, the electronic configuration of Ni2 positive ion is 18 Ar 3d8. 8 electrons present in the d orbitals of Ni2 positive will occupy in such a way that we shall have 3 of the 3d orbitals occupied by 2 electrons, while the remaining 2 3d orbitals are singly occupied as shown in figure. These are two ways in which the coordination complexes of nickel with coordination number 4 can be formed. If the complex involves sp3 hybridization, it will have tetrahedral structure. On the other hand, if the complex involves dsp2 hybridization, it will have a square planar structure, as shown below. In case the complex ion acquires tetrahedral structure, the hybridization is sp3. It means that the two unpaired 3d electrons are not affected. As a result, the coordination compound with sp3 hybridization will be paramagnetic, as in the case with Ni2 positive ion itself. However, the square planar structure which involves dsp2 hybridization requires one of the 3D orbit vacant for hybridization. However, the square planar structure which involves dsp2 hybridization requires one of the 3D orbital vacant for hybridization. This is possible only if the two unpaired 3D electrons are paired up. Pairing makes one of the 3D orbitals empty. During this exercise, no unpaired electrons are left and the complex should be diamagnetic. It has been experimentally observed that the complex NiCl42 negative is diamagnetic, which conclusively indicate that the hybridization is dsp2, and secondly it has no unpaired electrons as shown in figure 1.1. Second, formation of NiCl42 negative. The oxidation number of nickel in NiCl42 negative is +2. This is obtained by the loss of 2 electrons from the 4s orbital of nickel as shown in figure 1.2. Experimentally, the complex has been found to be paramagnetic corresponding to 2 unpaired electrons. It implies that the 3D orbitals are not distributed or disturbed, and the complex involves sp3 hybridization. As a result, the structure of the complex is tetrahedral as shown in the below figure. Third is formation of CuNS34 whole 2 positive. As inspection at the complex CuNS34 whole 2 positive reveals that the oxidation state of copper in the complex is +2. The resulting electronic configuration of Cu2 positive is 18Ar3d9. According to Hund's rule, the 9 d electrons occupy the 5 3D orbitals and the only one orbital is singly occupied. In order to accommodate for ammonia molecules around Cu2 positive, the metal ion exhibit two possible geometrical arrangements for the complex. If the complex is tetrahedral, it will involve sp3 hybridization and the complex will be paramagnetic. On the other hand, if the complex happens to be square planar, it will involve dsp2 hybridization and the complex will be paramagnetic again. Now a natural question arises, which of the two structures of CuNS342 positive is true, tetrahedral or square planar? Having this diagram, crystal structure determination of the compound has revealed that the complex CuNS342 positive has the square planar structure. It implies that dsp2 hybridization must be involved with one of the 3D orbital made available for hybridization. This can be done by promoting one electron of the 3D orbital to a higher energy vacant 4p orbital. Once the electron is promoted into the higher energy orbital, it becomes unstable and can be lost easily. It means that Cu2 positive complex can be easily oxidized to Cu+3 complex. Cu2 positive tends to be Cu3 positive plus ejection of electron. However, it is not true because Cu3 positive ions are practically unknown. In brief, the above representation of CuNS342 positive ion is inadequate. Although it explains the square planar geometry together with the magnetic moment of the complex, it fails to explain that Cu2 positive can be easily oxidized to Cu3 positive. This anomalous behavior can be easily answered if it is considered that the electrons in the 3D orbitals are not perturbed at all and the hybridization involves outer 4D orbitals. This model explains not only the square planar geometry together with magnetic moment but also the stability of Cu2 positive, which do not undergo easily oxidation to Cu3 positive by loss of electron. Fourth is formation of NiCO4. NiCO4 is a unique compound in which the oxidation state of nickel is 0. The electronic configuration of nickel having atomic number Z equals to 28 is 18Ar3D8 4s2. Since the coordination number of nickel is tetracarbonyl nickel is 4, the compound can acquire either of the two structures, tetrahedral sp3 or square planar dsp2. Since in both the cases 4s orbitals are used in hybridization, therefore 4s orbital must be made vacant either by promoting 4s electrons to higher energy orbital with spin unpaired, or by forcing 4s electron to occupy the vacant 3d orbital with spin paired. In the first case, where the 3d electrons are promoted to occupy higher energy 4d orbitals, the compound NiCO4 will be paramagnetic as the electrons are not spin paired. On the other hand, when the electrons are forced to occupy the 3d orbitals, the compound NiCO4 will be diamagnetic because the forced 4s electrons have no other option but to pair with the two unpaired electrons sitting in the 3d orbitals. Since the compound NiCO4 has experimentally been found to be diamagnetic, the nickel atom prefers to involve sp3 hybridization as shown below. Let us apply the postulates of valence band theory to explain the bonding in other coordination complexes with coordination number 6. Formation of CrNs363 positive complex ion. The oxidation state of chromium in CrNs363 positive ion is +3. The electronic configuration of chromium having atomic number 24 is 18Ar3D54s1. Thus, chromium in positive 3 oxidation state is formed by the loss of 1 4s and 2 3d electrons as shown. Two vacant 3d orbitals, 1 4s and 3 4p orbitals of chromium are hybridized to give 6d2sp3 hybrid orbitals. In other words, Cr3 positive provides 6 empty orbitals to accommodate 6 pair of electrons from 6 molecules of ammonia. The resulting complex CrNs363 positive involves d2sp3 hybridization and is octahedral. The presence of 3 unpaired electrons in the complex makes it paramagnetic. Second, formation of CONs363 positive. The electronic configuration of cobalt having atomic number 27 is 18Ar3D74s2. The oxidation state of cobalt in the complex is +3, which is obtained by loss of 2 4s and 1 3d electron. Thus, the electronic configuration of CO3 positive is 18Ar3D6 as shown below. In this arrangement, there are 4 unpaired electrons and 1 paired electron in the 3d orbital. In order to acquire octahedral symmetry, the complex should have d2sp3 hybridization. This can be achieved in two ways. The 2 electrons in the 3d orbitals are either paired up with the electrons in the other 3d orbitals, thus leaving the other 3d orbitals empty. On the 2 3d electrons can be pushed into higher energy vacant 4d or 5s orbitals. Since pairing of electrons require less energy than promoting to higher energy orbitals, the electrons prefer to pair up 2 vacant 3d orbitals, and 4s and 3 4p orbitals of cobalt are hybridized to give 6 d2sp3 hybrid orbitals. In other words, CO3 positive provides 6 empty orbitals to accommodate 6 pair of electrons from 6 molecules of ammonia as shown in figure 1.6. Since there are no unpaired electrons in the 3d orbitals in the complex sign CONs363 positive, it should be diamagnetic. Experimentally, it has been found that the complex is diamagnetic. Formation of COF6 3 negative. As already discussed, the electronic configuration of cobalt having atomic number 27 is 18Ar3D74S2. The oxidation state of cobalt in COF6 3 negative is +3, which is easily achieved by losing 2 electrons from 4s and 1 electron from 3d orbital. The electronic configuration of CO3 positive is 18Ar3D6. The complex ion COF6 3 negative has been found to be paramagnetic, which suggests the presence of unpaired electrons. However, this behavior is altogether different from what we observed in case of CONS36 positive. It amounts to saying that the octahedral symmetry in case of COF6 negative cannot be attributed to D2sp3 as it is found in case of CONS362 positive. In an effort to explain this distinct behavior, Lewis Pauling suggested that the complex COF6 negative is ionic and the metal ligand bonds are ionic. This appeared justified at that time in view of the highly electronegative character of F negative fluoride ion. However, it was soon discovered that other complexes like COS2O3F3, FeS2O6 positive, and NiS2O6 positive were found to be paramagnetic. Since the bonding between metal and water in these compounds cannot be ionic, it suggests that Pauling's formulation of ionic bond between metal and ligand is not correct. An alternative explanation was proposed by Hughes in 1937 to explain the anomalous magnetic behavior of COF6 negative by suggesting that the metal can use outer d orbitals for hybridization in place of d orbitals, which are inner orbitals. This formulation keeps the inner d orbitals undisturbed and use the outer 4d orbitals for hybridization as shown below. Thus, 6 sp3 hybrid orbitals are found or formed from 1 4s, 3 4p and 2 4d orbitals. 6 pairs of electrons are donated to the 6 vacant hybrid orbitals of the metal, forming 6 COF bonds as shown in figure 1.7. It is clear from the above discussion that the central metal atom or ion has the ability to use either inner n-1d orbitals or outer nd orbitals for hybridization, depending upon the ligands and the magnetic property of the complex. In case the coordination complex uses the inner n-1d orbitals for hybridization D2sp3, it is called inner orbital complex. On the other hand, if the complex uses outer nd orbital for hybridization sp3d2, it is called outer orbital complex. In case of inner orbital complex, the metal electrons prefer to pair up. As a result, the complex will be either completely paired or will have lesser number of unpaired electrons. This type of complex formed is called low spin complex. On the other hand, in case of outer orbital complex, the electrons of the metal prefer to remain unpaired. As a result, the complex will have more number of unpaired electrons. This type of complex formed is called high spin complex. In brief, outer orbital complexes sp3d2 high spin complexes, inner orbital complexes d2sp3 low spin complexes. Next is formation of MnCN6 4 negative. The electronic configuration of manganese having atomic number 25 is 18Ar3D5 4s2. The oxidation state in the complex is +2, which is obtained by the loss of 4s electrons. Therefore, the electronic configuration of Mn2 positive is 18Ar3D5, having this figure. The magnetic moment of MnCn6 4 negative has experimentally found to correspond to the presence of a single electron. This can be easily accounted for if the 4 3d electrons are paired up, leaving behind one unpaired electron along with 2 unoccupied 3d orbitals as shown above. Now 6 vacant orbitals, 2 3d, 1 4s and 3 4p, intermix together to give 6 sp3 d2 hybrid orbitals. These hybrid orbitals can house 6 pair of electrons from the 6 cyanide ions to give an octahedral symmetry. The complex MnCn6 negative shows reduced paramagnetic behavior corresponding to the presence of only one unpaired electron. What would you like to call this complex, an inner orbital or an outer orbital? This complex, or it is an example of low spin complex because of reduced magnetic moment value. Fifth is formation of FeS2O6 3 positive ion. The oxidation state of iron in the complex is +3. Electronic configuration of iron is 18Ar3d64s2. Electronic configuration of Fe3 positive is 18Ar3d5. The complex FeS2O6 3 positive has been found to be paramagnetic, and the magnetic moment corresponds to the presence of 5 unpaired electrons. It clearly indicates that the 3d electrons are not disturbed at all. In addition, the outer 4d orbitals are used up for hybridization. It means 1 4s, 3 4p and 2 4d orbitals are hybridized to afford 6 sp3d2 hybrid orbitals, which are occupied by 6 pair of electrons, one from each water molecule. Having this figure, 6 coordinate bonds are formed by donation of 6 electron pair from 6 H2O molecules. Thus, FeS2O6 whole 3 positive is an octahedral molecule with paramagnetic behavior. It is important to remember that geometry and hybridization go hand in hand. If you know the geometry of a complex, can easily know which hybrid orbitals the metal atom uses. The relationship between the geometry of the complex and the hybrid orbitals used by the metal atom or ion is nicely summarized in table 1.1. Limitation of valence bond theory. The valence theory, extended by Linus Pauling to coordination compounds in terms of orbital hybridization, was successful in interpreting the symmetrical shapes of most of the complexes. However, the theory failed to account for several properties associated with the complexes. For example, it fails to explain the color and spectra of the complexes. Second, it fails to explain the differences between measured and calculated magnetic moments, although the theory is successfully in predicting the number of unpaired electrons in the complex. It also fails to explain why the magnetic moment value varies with temperature. Fourth, the theory fails to explain to the relative stability of the complexes. Fifth, it fails to explain why some complexes are labile while the others are inert. Labile complexes are those in which one of the ligand can be easily displaced by another ligand. On the other hand, inert complexes are those in which the displacement of ligand is slow. Sixth is, it does not predict whether the 4 coordinate complexes species will be square planar or tetrahedral. For example, the decision about the geometry of nickel 2 species depends upon the value of magnetic moments as shown. Seventh, it considers Ni to be tetrahedral, whereas in fact it has octahedral symmetry. Eighth, The theory fails to explain why some metal complexes in a particular oxidation state are spin, while the other complexes of the same metal ion in the same oxidation state are high spin or low spin. For example, CONS3 6 3 positive and COF6 3 negative, in which cobalt is in +3 oxidation state. The former is low spin while the latter is high spin. Crystal field theory. Valence bond theory helps to understand the bonding in coordination compound. However, this theory suffers because it neither accounts for the color of the coordination compounds nor explains some complexes are high spin whereas others are low spin. Crystal field theory, on the other hand, it explains successfully the colors of the complexes as well as their magnetic properties. This theory was developed by physicists named H. Bethe and V. Black. Account for the color and the magnetic properties of hydrated salts of transition metals. Originally, crystal field theory was applied to transition metal ion in ionic crystal. That is why the theory is called crystal field theory. Chemists began to apply the crystal field theory to transition metal complexes in 1950, and since that time inorganic chemistry has become an excited field of research. Crystal field theory considers the central atom and the surrounding ligands as point charges. Point charges are electric charges that exist at a single point. It is important to note that point charge has neither an area nor a volume. According to crystal field theory, it is electrostatic attraction between the positive charge on the central metal ion and the negative charge on the ligand that holds the ligand to the metal ion. In brief, crystal field theory assumes the bond between the metal ion and the ligand as purely electrostatic. In case the ligand happens to be negatively charged, such as Cn negative, Br negative, etc., the interaction between the metal and the ligand is referred as ion-ion interaction. In case the ligand happens to be neutral molecule, it can be considered to have a dipole moment. As in ammonia NH3, the nitrogen in the NH3 acquires a negative charge delta negative and the hydrogen acquires a positive charge delta positive. In such cases, the interaction of the metal ion with the ligand referred as ion dipole interactions. The d orbitals and crystal field theory. Since d orbitals are frequently used in coordination compounds, it is important to study their shape and distribution in space. In order to understand crystal field theory, it is necessary to look again at the spatial orientation of all the 5d orbital relative to the position of ligand in the metal complex. The 5d orbitals that are designated as dxy, dyz, dzx, dx square minus y square and dz square. The boundary surface of these orbitals are given as shown according to this figure. One subset of three orbitals dxy, dyz, dzx are similar in shape and each consists of four lobes of high electron density lying between xy, yz and zx plane respectively. The lobes of these orbitals lie in between the principal axis. There is another subset of two orbitals dx square minus y square and dz square. The orbital dx square minus y square consists of four lobes that lie along the x and y axis. The orbital dz square consists of two lobes that lie along the z axis and though called torus in xy plane. It is important to point out that although dz square and dxy x square minus y square orbitals do not look like in shape, yet they are equivalent as far as their interaction with the metal ions are concerned. The unique shape of dz square orbital can be regarded as a linear combination of two orbitals. dz square minus x square and dz square minus y square. Each one of each is equivalent to dx square minus y square orbital as shown in figure 1.11. Since both the orbitals dz square minus x square and dz square minus y square have high electron density along the z-axis, the dz square orbital has a large amount of electron density concentrated along the z-axis. Since one of the component wave function is maximized along the axis dz square minus x square and the other along the y-axis dz square minus y square, the resultant dz square has a torus of electron density in xy plane. However, both the orbitals dz square minus x square and dz square minus y square do not have independent existence. Assumptions of crystal field theory. Crystal field theory is now more widely used than the valence bond theory. It considers the attraction between the central metal and the ligand in the complex as purely electrostatic. The basic assumptions of CFT are the following. First, the transitional metal ion is surrounded by a number of ligands with lone pair of electrons. Second, the ligands are treated as point charges. Point charges are electric charges that exist at a single point. It is important to remark that point charge has neither an area nor a volume. Third, the ligand may be neutral or negatively charged species. In case the ligands are neutral, it is the negative end of the dipole that is oriented towards the metal ion. That accounts for the electrostatic interaction. In case of negatively charged ligands such as Cl negative, Cn negative, the interaction between the central metal ion and the ligand is purely 100% ionic. Fourth, all the 5d orbitals of the isolated gaseous metal atom have the same energy. These 5 orbitals of the gaseous atom possessing the same energy are called degenerate orbitals. If a spherically symmetric field of negative charges is placed around the metal ion, all the 5d orbitals of the metal will be raised in energy as a repulsion between the negative field and the negatively charged electrons of the orbitals. In brief, the energy of the orbital is raised because of the repulsion between the field and the orbitals. In brief, the energy of the orbitals is raised because of the repulsion between the field and the electrons on the metal. However, the energy of the 5d orbitals will be still remain degenerating. If the electric field results from the influence of real ligands, the electric field is not spherical symmetrical because of finite number, usually 4 and 6, of ligands involved. In such a case, the d orbitals are not affected equally by the electric field of the ligands. We also noticed that the d orbitals have different orientation in space and therefore these orbitals will experience different interaction from the ligands. The orbitals lying in the direction of the ligands will experience greater repulsive interaction and consequently then energies will be raised. On the other hand, the metal orbitals lying away from the ligands will experience lesser repulsive interactions. As a result, their energies will be raised to a smaller extent. In summary, the energies of the 5d orbitals of the metal are split due to electric fields generated by the ligands surrounding the metal. The splitting of energy of the 5d generate d orbitals of the metal ion into two different sets of orbitals into different energies in the presence of electric field of ligand is called crystal field splitting. Fifth is the number of ligands coordination number surrounding the metal affects the energies of the 5d orbitals. It means that the crystal field splitting will be different with different coordination number. 6. The properties of the coordination compounds such as magnetic properties and color of the compounds can be easily explained in terms of splitting of d orbitals in different crystal fields. Thank you.